Hello. In this module, we are going to analyze a slew of open-steady devices where only a single flow passes through the system. So let's start with a very generic single flow device. As we show in this diagram, a flow is going into the system, coming out. It's operating at steady state. Some heat transfer and work transfers are possible. Of course, the direction are shown in the positive direction. If we use the mass, energy, and entropy equation, let me just do one more time. We have already derived this equation. This is the most generic equation for mass. Steady state means this goes out, and there's a single flow. Therefore, m dot I must be equals m dot E, or m dot 1 in this case equals m dot 2, and we'll call that just as m dot. So many kg per second of flow is passing through the system. Very easy. How about the energy equation? Similarly become energy carried by the flow, energy transported out by the flow, heat that enters, and external work that leaves the system. Steady state. Single flow. So by rearranging, we can do that, and substituting m dot I equals m dot E, we get m dot J inlet plus Q dot equals m dot J exit plus W dot external. So that means energy in must be equals energy out. Just like this means mass in equals mass out. So you can see that energy is entering to the with the flow and heat, and coming out through the exit flow and work. If we write the entropy equation, it would be similar. So okay, just I'm writing a single flow here. So there's no need for a summation. Well, if it is steady state, again, the equation becomes m dot Si, the entropy that is flowing in with the flow, plus the entropy that enter with heat must be, plus there's another term, entropy can also be generated inside the system, and that must be equal to the entropy that come out of the system. This is m dot, the same as m dot E and I, m dot Se. So this is a straightforward thing for any device. Notice that we haven't said it's a turbine. It could be a turbine, a compressor, a pump, a nozzle, and we're going through various systems with specific examples soon. But important to understand that we can intuitively write this equation. This is the entropy that is in, and plus the generated must be equals out. Okay. Also remember that the entropy generation is a measure of friction in the system, or the measure of irreversibility, to be precise. So in actual device, many times there will be a lot of friction, but ideally it is possible that there is no friction in a device. So let's concentrate on a subset of these single flow devices which are adiabatic and frictionless. So I'm simplifying this single flow a steady device diagram with no heat transfer. So this is an insulated system, no heat transfer. It only transfers external work. Example could be a pump, could be a turbine. We'll come into those in a minute. So if we write the energy equation for this device, obviously you'll get the energy that comes in, m dot J1 plus, there's no heat coming in, must be m dot J2 plus W dot external. In other words, we get a formula for W dot external to be m dot J1 minus J2. Now, if we use the entropy equation, what do we get? M dot S1, there's no heat coming in, but there could be entropy generation. Well, let's put the heat term, and we can take it away, must be m dot s2. So in this special kind of device, if it is adiabatic and internally reversible, in other words, so let's write down the condition. Adiabatic means heat transfer is 0, and internally reversible means there is no friction inside, so S dot gen inside the internal boundary must be 0. That produces a special class of device. Can you see that? It's called isentropic device. So in case, suppose it's a turbine, the amount of work produced will be maximized. If it's a compressor, the amount of work consumed will be minimized. So such devices, in actual device, what happens is that suppose this is the real device. This is the isentropic device, and if we have an actual device and do this analysis again, we cannot set S dot gen to 0 anymore because of friction, S dot gen will be positive. So if there is friction inside the device now, the exit state, we cannot expect it to be the same. So we'll represent the exit state with a new state number for the actual device. Let's call it state 3. So this is a neat way of expressing the isentropic and the actual device. 1 to 3 will be actual device, and isentropic device that we just studied in the previous slide goes from 1 to 2. The same device, if you use a magic wand, the exit state will be 2 because there is no friction anymore, and in the real device it will be state 3. But as you can see, so the external work for the actual device will be given by m dot j1 minus j3. And isentropic device, of course, we already did that, m dot j1 minus j2. The ratio between them is called isentropic efficiency. What does it mean? Is the ratio of the actual and isentropic work transfer. It's called isentropic efficiency for a compressor or a turbine. For a turbine, so we represent it by, it's called eta S. For a turbine, so for a turbine, the efficiency definition will be, so you understand that isentropic turbine will be more ideal, it will produce more work, so the bigger number goes at the bottom. So W dot external isentropic will be at the denominator, and W dot external actual will be at the numerator. In case of a compressor, the definition will be just reversed, because in a compressor, the isentropic work will be less. Anyways, so let's go over a few specific devices using some animations, and you will get the idea of the mass, energy, and entropy balance for each device. That will be our goal right now. And as we solve problems, it will become even more clear how do we go about analyzing single flow open steady devices. So let's go to chapter 4, single flow. Let's find a turbine. So how do we analyze a turbine? First of all, what is a turbine? Well, we don't have to know the details of a turbine. Just go over the boundary and it will become abundantly clear what's going on. There's a flow that comes in at the inlet state and it goes out at the exit state. And as it goes through the internal nozzles and blades, what it does, it makes this shaft turn. Essentially, when the working fluid, which could be steam, which could be hot gases, which could be liquid water, when they go through nozzle, they come out very fast, and then they hit the blades. And as you can see, the nozzles are kind of fixed to the casing, and the blades are connected to the shaft of the turbine. and as a result, as the blade turns, the shaft turns, producing shaft work. As I said, the details are not important to us. All we need to know what are the input, output, and what happens across the boundary. So let's look at the mass equation. As you can see, the mass equation becomes, so our concentration will be figuring out the mass, energy, and entropy equation for each of these devices. So mass is, as we said, what goes in is what coming out. As you can see, clear cut, goes in, comes out. Energy equation, again, is adiabatic. Most turbines are adiabatic, but in a given problem, it will be given to us. So as you can see, the energy equation becomes what goes in is what comes out. But then the external work, we're calling it W dot T, the turbine work. So turbine work is same as external work given by this formula. And if we neglect KE and PE changes, J becomes H. Likewise, the entropy equation, as you can see, we already discussed for a generic device. You can see for this turbine, this is what entropy that goes in. And if it is isentropic, that means this goes to zero. No, it's reversible. Therefore, no entropy generation, no heat transfer, and we get back isentropic. We prove that it's isentropic. It's isentropic when there is no heat transfer and no friction in the system. So you got to kind of memorize that for any device. This will be true. Okay, and the turbine efficiency, as you can see, we are comparing an actual turbine with ideal turbine, and in this HS diagram is very similar to TS diagram. And as you recall, the constant pressure lines kind of goes up. In the superheated region, you remember how the constant pressure lines look like. So higher pressure means the line will be on the upper one will be the higher pressure. So for a gas, the constant pressure lines look like this, as in the case of superheated vapor. So if it's isentropic turbine, entropy doesn't change. As you can see, the state comes vertically down as it produces power. In an actual turbine, on the other hand, if you use the entropy equation, you can see because of entropy generation, the entropy at the exit will be higher than entropy at the inlet. And we saw that. If you go back in the entropy equation and say, if you say that, well, this is not zero, then as you can see, if this term is there, you can show that SE will be greater than SI, because entropy generation is always positive, or at the best, zero. Okay, so let's visit some other devices. Let's see how a nozzle, how do you figure out the equations for a nozzle? Again, what is a nozzle? A nozzle is a device whose purpose is to increase the kinetic energy, increase the velocity of a fluid passing through it. So as the fluid enters, it passes through sometimes a converging shape, sometimes a converging diverging shape in case of a supersonic nozzle. Again, those details are not important to us at this moment. We concentrate on what happens around the boundary. So to set up the equation, we immediately recognize that the mass equation is the same as in turbine, no difference. And energy equation, there is no external work. There could be heat transfer, but mostly in an adiabatic nozzle, Q dot equals 0.2. So what we get is that the flow energy at the inlet and exit are equal. However, an important simplification comes if we recognize that when we expand J in terms of H and KE, that the inlet kinetic energy is small compared to exit kinetic energy. First of all, in a nozzle, we cannot just say neglect kinetic energy changes like we did in case of a turbine. Well, the reason is the exit kinetic energy is the desired quantity. We want to find what is the exit velocity. If you say that is zero, we throw away the problem. So, but however, because the velocity, the purpose of the nozzle is to increase velocity, and kinetic energy goes to the square of velocity. So therefore, the inlet kinetic energy can be easily neglected without changing the result much. And as you can see, this equation, when you solve for velocity, we get a solution for exit velocity. Again, if you use the entropy equation, adiabatic and adiabatic and reversible, there is no friction, makes the nozzle isentropic. Just like turbine, we could also define a nozzle efficiency, but right now this is enough to just do a mass, energy, and entropy analysis of all sorts of devices. Again, it's just a matter of repetition, but I think you should get the idea that we can understand a device. Suppose you never heard of a device called diffuser, and I just tell you this. All the purpose of the diffuser is to slow a flow down so that we can increase the pressure of the flow. So notice that in a nozzle, the velocity expands, the pressure drops. In the case of a diffuser, the kinetic energy slows down, the flow slows down, and the pressure increases. So let's see if we can figure out the mass, energy, and entropy equation for a diffuser, adiabatic diffuser. Again, the mass equation is exactly the same for any single flow device, is the same mass equation. Same energy equation, except we can simplify. There is no heat transfer and work transfer. Therefore, J's are equal. And notice in case of a diffuser, we can neglect the exit kinetic energy, simplifying things. Therefore, we can get an expression from here. From here, we can relate the enthalpies at the inlet and exit. Again, the entropy equation for an adiabatic frictionless flow becomes isentropic. And if we solve a specific problem, you can see that from this information, these equations will connect your exit state to inlet state, and therefore we can figure out the state of the exit state and hence the pressure at the exit state. Okay, so let's see what other devices we can quickly go over. Let's go over a compressor, which should be very similar to turbine. What does a compressor do? It increases the pressure of a gas or a vapor, as opposed to a pump. The purpose of a pump also is to increase pressure, but the working fluid is a liquid. So it's something to remember. So in case of a compressor, again, look at this repetition. The mass equation is exactly the same. What comes in goes out. Energy equation is almost the same as a turbine, actually exactly the same, except the compressor work, if we call it W dot C, a positive number, then external work will be negative W dot C. So as you can see, W dot C becomes M dot HE minus HI. And it can be intuitively understood. Notice the energy that comes out here at the end of the compressor must be equals the energy that goes in with the mass plus the energy that we put in as W dot C. In other words, you can see that from intuitive idea, in a compressor, energy is going in, M dot Ji is the energy that goes into the inlet, and then we are adding W dot C amount of power, shaft power, and what comes out is M dot Je. So that's the energy equation. So that will tell us, this equation will lead us to find how much compressor power is required to meet given pressure rise, etc. If you go for a pump, it will be almost very similar, because if you think about it, a compressor and pump, as far as the governing equations are concerned, are no different. Again, this is our mass equation. What goes in comes out. And the energy equation here, we are calling external work, obviously will be negative, because again, pumping power is going into the system, just like a compressor. So W dot P is given by the enthalpy difference times mass flow rate. And if it is adiabatic and frictionless, as you can see, the pump also can be isentropic. So I think we have covered several devices. If you go over chapter 4 in your textbook, you can get more details and read up on each device and see how the analysis is done. Just a quick mention of a concept, of an advanced concept that I just want to cover for the sake of completeness. It's called internally reversible devices. There are some amazing insight you can get if we understand what graphically a TS and PV diagram means for a single flow device. So here we show a very colorful single flow device. The flow comes in, goes out. There is probably some heat transfer and work transfer in this device possible. We also will assume the system is internally reversible. That means there is no friction inside the device. And in the TS diagram, we are just arbitrarily showing a PC fluid, but the fluid doesn't have to be a phase change fluid. It could be gas or any other flow or liquid. So what we are trying to say that if such a device can be broken into small sections, like 1, 2, suppose we go and analyze, instead of the entire device, an element. So we took an element. The idea is that this slice of a device handles the same mass flow, and there's a tiny bit of heat and work transfer involved. But if we sum up all these tiny slices, they add up to the entire device. So now for this tiny element, as you can see, if I use the entropy equation, the heat transfer becomes dq instead of q dot, and the temperature in this slice of thing is the same. The boundary temperature is same as temperature everywhere, because we have such a thin slice, and we are talking about an internal system. If we do a little manipulation, we get an equation which says that heat transfer in this internally reversible device can be connected with TDS, that is the area under the TS diagram. So if we integrate this equation, we reach the device. So we reach a very simple conclusion that in a single flow device, if you can draw the TS diagram and you can show where your inlet and exit state is, then the area swept under is proportional to heat transfer. So in other words, this concept doesn't really allow us to solve a problem more easily, but it allows us to visualize a problem. We just look at the TS diagram. Remember the pipe problem we solved with fluid getting heated up to saturation, liquid to saturated vapor, then with superheated vapor. You can see here why the energy transfer, to heat up, you can see that most of the heat will be used in converting liquid to vapor, as you can see from the area under the diagram. This concept will become more important in ME 351 when we cover specific large systems such as a power plant, etc. Just like heat transfer has a graphical meaning, the external work transfer also has graphical meaning. Again, over there, if you go for an element the same way and use the energy equation and recognize that the work and heat transfers are D amount, because we are talking about a thin slice, and then we substitute the finding of the previous entropy equation and do some manipulation, we come up with a formula for the external work in terms of the PV diagram. If we integrate that, what it produces is external work is given by integral VdP and change in kinetic and potential energy. If change in Ke and Pe are negligible, then the meaning becomes extraordinary. It says that the work produced in a device or work consumed in a device, if there's no friction inside, and by the way, it's not such an ideal thing. No friction inside will give you a good idea about what a real device does. So in this kind of a device, you can see that the integral VdP tells us how much work will be transferred. In the PdV diagram, integral VdP is the work on this shaded area. Just like a PV diagram, you can find boundary work, finding the area subtended on the V-axis. For work producing or work consuming open steady devices, it is the transverse area that is shown in this animation that is proportional to the work transfer. So if you go back to the animation of the pump, you will find that this area is very small for a pump, because for a liquid, the specific volume is very small. So for a pump, this diagram probably will look something like this. That means very little bit of work is needed for a pump. As opposed to a compressor, you will find the specific volume will be much higher on the average, and the work required for the same increase in pressure will be much higher for a compressor than in a pump. And this kind of physical explanation is not possible unless you understand this internally reversible device. Well, enough about this abstruse theory. We'll go and solve a few specific problems, say involving a turbine, involving a nozzle, etc., and you'll get a better handle. But I must tell you that mastering the open steady devices, especially single flow devices, is so important because they constitute the heart of thermodynamic devices. All the practical devices you see, I would bet that almost 80% of them will involve some sort of open steady device.